Are you struggling to master the concept of moment of inertia on the FE exam? In this week's Pass the FE exam video, we'll reveal the secret to overcoming this challenging topic and help you achieve success on your FE exam. We'll start by revisiting the basics of inertia and then dive deeper into the essential topics like centroidal area and the parallel axis theorem. These concepts are critical for understanding how the moment of inertia works and will prepare you to handle the different scenarios that you're likely to encounter on the FE exam. This problem was created and solved by mechatronic engineer Shante Thunderspay. Let's jump right into it.
In today's question, we are presented with an I-beam, and we're asked to calculate its moment of inertia about its centroidal x-axis. We're also given a list of possible answers, all presented in millimeters. So straight off the bat, we know that we'll be sticking to this unit in our calculations to keep things simple and prevent possible conversion mistakes. Now, before we jump into the solution to this problem, let's review some key concepts so you have a better understanding of the theory behind this question. The area moment of inertia is a parameter that defines how much resistance a shape, like that of the cross-section of a beam, has to bending due to its geometry. For example, when we apply a concentrated load to the center of three simply supported beams, like we have here, we get an intuitive feel for how the beams would react under this stress. In this case, the beams are bending about their own central axis, referred to as their centroidal axis. The beam to the left would deform easily under this stress due to its cross-section having a small inertia or resistance to bending. But when you look at the second or third beam, they have larger inertias, making them more resistant to bending in this plane. This resistance to bending is influenced by the distribution of area about the bending axis, meaning when a shape has more of its area distributed further away from the bending line, like with our I-beam, it's also less likely to bend. However, it's important to realize that this concept of inertia is relative. In other words, the inertia of a shape can only be taken with respect to a defined axis. So here's a summary of the different axial cases that you might expect to see on the FE exam. First off, you may be asked to calculate a shape's inertia about its centroidal axis. And as we've shown before, this axis is positioned through the geometric center of the shape. Here, we name our axis XC and YC, with C referring to the centroidal axis. In the second case, you may be asked to calculate the cross-section's inertia about the coordinate axes, or X or Y axes, as shown here. Lastly, you may be asked to calculate the shape's inertia about any axis positioned at a predefined point. It's important to identify which of these cases you're working with while tackling these problems, since this will later help you distinguish which formulas to use. If you're working with a basic shape, like the rectangle we have here, the FE handbook conveniently defines all the equations we need to calculate the shape's inertia about the X and Y coordinate axes, as well as about its own centroidal X and Y axes. They list these formulas for a range of simpler shapes like circles and triangles, and even for some more complex shapes like parabolas. We can utilize these formulas to calculate the different inertias we're interested in. However, what's very important here is that you're familiar with the notation used by the handbook. In other words, be sure to know that IXC and IYC refers to the shape's inertia about its own centroidal axis, while IX and IY refer to its inertia about the global X and Y axes. In the case of the I-beam, we're working with a relatively complex shape when compared to something like a rectangle. But luckily, there's a theorem that allows us to tackle these complex composite shapes, and it's referred to as the parallel axis theorem. The FE handbook provides us with a useful definition stating that the moment of inertia of an area about any axis is defined as the moment of inertia of the area about a parallel centroidal axis, plus a term equal to the area multiplied by the square of the perpendicular distance from the centroidal axis to the axis in question. To put this into simpler terms, we can refer back to the third axial case we had earlier. The theorem states that we can calculate the inertia of the shape about this arbitrary axis, and we'll refer to this inertia as Ix. This is done by adding the shape's centroidal inertia to a second term, consisting of the distance from this arbitrary axis to the shape's centroidal axis, multiplied by the shape's area. This theorem allows you to calculate the inertia of a shape about any axis, and consequently, it also allows for the evaluation of more complex shapes, like our I-beam. So without further ado, let's get started on our problem. First, we need to recognize that this seemingly complex shape can be split up into 3 smaller rectangles. In other words, if we can manage to calculate the moment of inertia for each individual shape about the centroidal x-axis, and we sum these values together, we'll have the total inertia of the shape. Second, we need to figure out where the centroid of this asymmetric shape is located. And here we're referring to the centroid of area. Remember, since this cross-section has a larger area closer to its base, its centroid will also be shifted towards the bottom. We can define the centroid of the I-beam as y bar, a distance measured from the x-axis. To find the position of this centroid, we'll need to calculate the area of each rectangle, as well as the distance from the reference x-axis to each respective rectangle. The centroid can then be found as the sum of all areas multiplied by their distances, and then divided by the sum of all areas. We start off by calculating the area of our top rectangle, which would be its base multiplied by its height, or 120 by 15 millimeters. This rectangle's height from the x-axis to the centroid can be found to be 137.5 millimeters. We can then go ahead and define these values for our other 2 shapes to find the centroid of the I-beam. The second rectangle has an area of 100 by 15 millimeters, and its height above the x-axis is 80 millimeters. Finally, the third rectangle has an area of 180 by 30 millimeters, while its height is equal to 15 millimeters. We substitute these values into our equation to find that the I-beam has a centroid of 51.55 millimeters from the x-axis. Now that we know where the centroid of the shape is located, we can continue by calculating the respective inertias of each shape about this axis. And this is where the parallel axis theorem can come in quite handy. We use this theorem to calculate the individual inertias of each shape about the centroidal axis at 51.55 millimeters. Starting off with the inertia of the orange rectangle, the theorem requires that we first calculate the moment of inertia for this shape about its own centroidal axis. For this, we consult the FE handbook and find the formula to be base times height cubed divided by 12. We then substitute the base as 120 millimeters and its height as 15 millimeters to find that the rectangle has an inertia of 33,750 millimeters to the power 4. Now we need to find a value for dy1, but first let's recall that this parameter is defined as the distance between the center of the shape to the axis of interest, and in our case this is y bar. So intuitively, we can calculate this value by subtracting y bar, or 51.55 millimeters, from y1, or 137.5 millimeters, to find that dy1 has a value of 85.95 millimeters. We can now substitute these values into our parallel axis theorem, along with the area of the shape, to find its inertia as 13.33 times 10 to the power 6 millimeters to the power 4. We now repeat this process for the other 2 shapes. We start by calculating the green rectangle's inertia about its own centroidal axis using the same formula as before. By substituting the base as 15 millimeters and the height as 100 millimeters, we find that it has an inertia of 1.25 times 10 to the power 6 millimeters to the power 4. Next, we calculate this shape's distance from the centroidal axis by subtracting its central height from that of the centroidal axis as before. to find dy2 as 28.45 millimeters. When we then substitute these values back into the parallel axis theorem, we find that this section has an inertia of 2.46 times 10 to the power 6 millimeters to the power 4 about the I-beam's centroidal axis. And last but not least, we find the inertia of the blue rectangle. For this, we'll use the same formula as before to find that it has an inertia of 405,000 millimeters to the power 4 about its own centroidal x-axis. And when inspecting its distance from the centroidal x-axis, we find dy3 as 36.55 millimeters. When we substitute these values into our parallel axis theorem one last time, we find that the blue rectangle has an inertia of 7.62 times 10 to the power 6 millimeters to the power 4 about the centroidal axis. All that's left to do now is to add these values to find the total inertia of the entire shape. In doing so, we finally find the inertia to be 23.41 times 10 to the power 6 millimeters to the power 4. And that wraps up our problem. The correct answer is D. When attempting multiple choice questions, always take a moment to carefully review all the options before making your final selection. At first glance, you might have been tempted to choose A here. To wrap up, let's review the concepts covered today. We wanted to calculate the I-beam's inertia about its centroidal axis. To do this, we first had to find the centroid of the compound shape using the areas and relative distances of each rectangle. This point defined the centroidal axis for the system. Next, we calculated the inertias of each shape about the centroidal axis by utilizing the parallel axis theorem 3 times, once for each rectangle. But in order to apply this formula, we also had to compute each shape's inertia about its own centroidal axis. And we did this by using the readily available formulas provided by the FE handbook. Finally, we combined these values to calculate the beam's total moment of inertia about its centroidal axis. And there you have it. By breaking down the problem step by step, we used solid theory and practical application to solve for the I-beam's moments of inertia.
I hope you found this week's video helpful. In upcoming videos, we will answer more of your FE exam questions and run through more practice problems. Pass the FE exam will publish videos weekly, so please be sure to click that subscribe button as you'll get expert tips and tricks including practice problem solutions weekly to ensure that you pass the FE exam. And I encourage you to ask questions in the comments that I'll read and respond to in future videos. If there's a specific topic that you want me to cover, or maybe a question you need answered, Pass the FE exam will have you covered. I'll see you next week on Pass the FE exam.